Hi all, myself Kartika. Today we are going to see about parsers. Parsing is the second phase of the compiler. So far we have discussed about lexical analyzers. The job of lexical analyzer is to generate tokens. After the end of lexical phase, the compiler start viewing our high-level language program in the form of tokens. So it won't see like what we write form of a program like int, declaration path or printf statement, looping statement or anything like that. So everything will be converted in the form of tokens. So compiler after a lexical phase won't see the program as high-level language program that we fed into the computer. It will see the program in the form of a tokens. So for we know how to generate tokens for a program. If it is an identifier, we give a name as ID followed by some attribute value. If it is a keyword, we specify the keyword itself. If it is a constant value, we know how to specify it in the form of a token. So after lexical phase, everything will be viewed in the form of tokens. This tokens is given to the next phase. What is the next phase? Next phase is syntax analyzer. So syntax analyzer is the second phase of the compiler. So in today's lecture, we are going to discuss about the procedures used by parsers to generate a parse tree using context-free grammar. So this is a new type of grammar that we are going to see today. So initially we will be discussing about the role of parser in compilation. Next, we are going to express the rules, how our syntax rules can be framed using context-free grammars. Then finally, we are going to say about how ambiguity in grammar is dealt. Let us see everything in detail in our lecture. Syntax analysis or parser, as I told before, is the second phase of the compiler. We have already seen that a lexical analyzer can recognize tokens with the help of regular expressions and pattern rules. But a lexical analyzer cannot check the syntax of a given sentence due to the limitations of the regular expressions. And also, regular expressions cannot check balancing tokens such as parentheses. Therefore, our parser phase uses context-free grammar, also known as CFG. So, this context-free grammar is recognized by push-down automata. So, in our lexical analyzer phase, we have seen about finite automata, DFA and NFA. And here, in context-free grammar, we are going to use push-down automata, which recognizes our context-free grammars. So, the parser or syntactic analyzer obtains a string of tokens from the lexical analyzer and verifies that the string can be generated by the grammar for the source language. And also, it reports any syntax errors in the program. It also recovers from commonly occurring errors so that it can continue processing its input. So, normally our syntactic analyzer creates a syntactic structure of the given source program. So, the syntactic structure is mostly known as parse tree. So, that's why we call syntax analyzer as parser. The syntax of a programming is described by a context-free grammar, CFG. So, we will use Backus NOR form notation for describing CFG. The syntax analyzer checks whether a given source program satisfies the rules implied by a context-free grammar or not. If it satisfies, the parser will create the parse tree of the program. Otherwise, the parser will give the error messages. So, the syntax analyzer will check the source program whether the source program is satisfying the rules implied by our context-free grammar. If it satisfies, parse tree will be generated, else error messages will be generated. Okay. So, next let us see about the position of syntax analyzer during the compilation process. So, a syntax analyzer, otherwise called as parser, it takes the input from the lexical analyzer in the form of token string. The parser analyzes the source code against the production rules to detect any errors in the code. So, that production rules is in the form of context-free grammar. So, the output of this phase is a parse tree. This way, the parser accomplishes two tasks. First is parsing the code, and second one is generating a parse tree and looking for errors. So parse tree and errors will be the output of this phase. Parsers are expected to parse the whole code even if some errors exist in the program. Parsers use error recovering strategies, and we will discuss about the error recovering strategies in the later chapters. Next, we are going to see about the jobs performed by the parser. So the first job is parser verifies the structure generated by the tokens based on the grammar. Then it constructs the parse tree. Then it also reports the errors. If an error is there, it performs error recovery also. So these are the jobs performed by the parser. Next, we are going to see about the issues faced by parsing phase. So parser is mainly involved in error detection and error recovery, but parser cannot detect errors such as variable redeclaration. So in our program we may redeclare a variable, so that cannot be detected by parser. Then variable initialization before use. So this initialization can also be not detected by the parser. Then data type mismatch for an operation. While performing an operation, if a data type mismatches, like for example, consider that we are going to perform an operation like A is equal to B plus C minus D. Here A equal to integer and B equal to 5. C is equal to 10, whereas D is equal to 5.5. So A, B and C are integers, whereas D is a floating point value. If I substitute here, it will be 5 plus 10 minus 5.5. So what is the answer? 15 minus 5.5, it is 9.5. So this 9.5 is what? It is a floating point value, whereas A is what? A belongs to the data type integer. So integer cannot store floating point data. So this will be converted to an integer data and it will be stored inside A. So this kind of data type mismatch cannot be detected by the parsers. And all these above issues are handled by the next phase, that is semantic analysis phase. Next, we have told about context-free grammar. So context-free grammar is a superset of our regular grammar. As depicted in this picture, it is a superset of our regular grammar. So it implies that every regular grammar is also context-free, but there exist some problems which are beyond the scope of regular grammar. So context-free grammar is a helpful tool in describing the syntax of the programming languages, right? Let us see in detail about what is meant by context-free grammar. So context-free grammar gives a precise syntactic specification of a programming language, and while designing a compiler, designing grammar is the initial phase, and this grammar can be directly converted into a parser by some tools. Languages that are generated by context-free grammars are called context-free languages. So context-free grammars are more expressive than finite automata. For example, if a language L is accepted by finite automata, then L can be generated by context-free grammar. But beware that the converse is not true. Next, let us see the definition of context-free grammar. So context-free grammar has 4 parts and it is given by grammar G is equal to V, sigma, P and S. So these are the 4 components of context-free grammar. So what is V? So a set of non-terminals is called as V. So non-terminals are syntactic variables that denote sets of strings. The non-terminals define sets of strings that help define the language generated by the grammar. Then what is sigma? Sigma is nothing but terminal symbols or a set of tokens. So terminals are the basic symbols from which the strings are formed. Then P is nothing but productions. So the productions of a grammar specifies the manner in which terminals and non-terminals can be combined to form strings. So each production consists of a non-terminal on the left side of the production. For example, this is a non-terminal on the left side of the production and an arrow and a sequence of tokens or terminals on the right hand side of the production. So this is a production. So we have a non-terminal on the left hand side and terminal symbols in the right hand side. Next, yes. Yes is the start symbol. So one of the non-terminals is designated as the start symbol from where the production begins. The strings are derived from the start symbol by repeatedly replacing a non-terminal by the right hand side of a production for the non-terminal. Let us see an example for it. So we take the problem of palindrome language. So this cannot be described by means of regular expression. So palindrome language L is given by word such that word is equal to word exponential of R. So this is not a regular language and it can be described as a context-free grammar. We know the definition of context-free grammar is given by G is equal to V, sigma, T and S, where V is nothing but non-terminals, set of non-terminals, Q, Z and N, and sigma is terminals. We are having terminals like 0, 1. So the productions we are using is P is equal to Q turns to Z or Q turns to N, Q turns to epsilon, Z turns to 0, Q0, N turns to 1, Q1 and start symbol is our Q. So now let us describe the palindrome language using this grammar like. So first let me start with the start symbol. Q turns to Z. Instead of Z I will replace with 0, Q0. So 0, Q0. So instead of this Q I will replace with N. 0, N, 0. So instead of N I replace with 1, Q1. 0, 1, Q1 and 0. And instead of this Q I will replace with epsilon. So 0, 1. Epsilon means it is null value. So it is considered as nothing. So I am just leaving it. So 0, 1, 1, 0. So this is what? This is a palindrome. See, if I read from this side it is 0, 1, 1, 0 and also if I read from the opposite side it is 0, 1, 1, 0. So this is a palindrome. So whatever strings you apply, you will definitely get a palindrome for this production rules. So this palindrome can be defined by using our context-free grammar. Next we are going to see about derivations. So a derivation is basically a sequence of production rules in order to get the input string. So during parsing, we take two decisions for some sentential form of input. One is deciding the non-terminal which is to be replaced. We have to decide which non-terminal has to be replaced. Next, we have to decide the production rules by which the non-terminal will be replaced. Okay. So first we have to decide upon the non-terminal. And after choosing the non-terminal, we have to decide by which production we have to replace that non-terminal. Okay. So these are the two decisions we take during parsing. To decide which non-terminal to be replaced with production rules, we can have two options. One is leftmost derivation and rightmost derivation. First, let us see in detail about leftmost derivation. So leftmost derivation is nothing but if the sentential form of an input is scanned and replaced from left to right, then it is called as leftmost derivation. So the sentential form derived by the leftmost derivation is called left sentential form. Then what is meant by rightmost derivation? So if we scan and replace the input with production rules from right to left, then it is known as rightmost derivation. So the sentential form derived from the rightmost derivation is called right sentential form. Now let us see examples for leftmost derivation and rightmost derivation. See here I am having the production rules as E turns to E plus E, E turns to E star E, E turns to ID. And the input string is ID plus ID star ID. Now how can we write a leftmost derivation? So first let me start with the production E turns to E star E. So in the leftmost derivation I have to derive from left to right. So first let me start replacing the leftmost non-terminal E. So instead of E I am going to replace it with E plus E. So E plus E star E. Then next I am going to replace the next leftmost non-terminal, this E. So instead of E I am going to replace with E turns to ID. I am going to replace with ID. So ID plus E star E. So now we have replaced the non-terminal to a terminal. Next I have to shift to the next leftmost non-terminal. So the next leftmost non-terminal is this E. So I am going to convert this E to the terminal ID. So ID plus ID star E. Then finally the next leftmost non-terminal is this E. I am going to convert this non-terminal as ID. So ID star ID star ID. So finally we have obtained our input string. So this is called as leftmost derivation. So here you can notice that the leftmost non-terminal is always processed first. Next, rightmost derivation. The same example I am taking. See now let me take the production as E turns to E plus E. So what is the rightmost non-terminal? This E. So instead of E I am going to replace with E star E. So E plus E star E. Then I am going to replace the rightmost non-terminal this E with ID. So E plus E star ID. Then the next rightmost non-terminal to be replaced is this E. I am replacing it with ID. So E plus ID star ID. Then the remaining non-terminal is this E. I am replacing it with ID. So ID plus ID star ID. So finally we have obtained our input string. So this is rightmost derivation. If we start processing the leftmost terminal first, if we start processing the leftmost non-terminal first, it is leftmost derivation. If we process the rightmost non-terminal first, it is rightmost derivation. Parse tree. Parse tree is nothing but it is a graphical depiction of a derivation. It is convenient to see how strings are derived from the start symbol. The start symbol of the derivation becomes the root of the parse tree. So always start symbol becomes the root of the parse tree. Then all leaf nodes are terminals and all interior nodes are non-terminals in a parse tree. And in order traversal gives the original input string. So we have to follow level by level order traversal for obtaining the original input string. So this is a small description about how a parse tree could be formed. Now let us see an example of forming a parse tree. I have taken the same leftmost derivation A plus B star C. So the production rules are, so the leftmost derivation we have seen in the last slide. So the same thing I have taken here. So how we can generate a parse tree? So for this production I am going to generate a parse tree. So E is our start symbol, then E, and here star, and here E. Okay. So this is our first production. Next we have to replace this E with E plus E. So I am going to replace this E with E plus E. The next step E plus E. What is the next production? We have to replace this E with ID, and I am replacing this E with ID. Next I have to replace this E with ID. So in the next step I am replacing the next leftmost non-terminal E with ID. Then finally the last non-terminal E will be replaced with ID. So finally we have obtained our input string ID plus ID star ID. So this is our input string. So this is how a parse tree can be generated. So a parse tree depicts associativity and precedence of operator. The deepest subtree is traversed first. Therefore, the operator in that subtree gets precedence over the operator which is in the parent node. Then there occurs a problem called ambiguity in grammar. So a grammar G is said to be ambiguous if it has more than one parse tree. So more than one leftmost derivation or rightmost derivation for at least one string, then that grammar is said to be ambiguous grammar. For example, if we have a production like this, E gives E plus E, E gives E minus E, and E gives ID. For the string, ID plus ID minus ID. So this is our string. So the above grammar generate two parse trees. So one parse tree is E, E plus E. Then this E can be replaced with E minus E, and this can be replaced with ID, ID, ID. So this is one kind of leftmost derivation, and next we can also provide rightmost derivation for the same production. So E turns to E minus E, and this E can be replaced with E plus E. Then we replace E with ID, then this E with ID, this E with ID. So for the same string we have obtained, so this is what? This is rightmost derivation. So for the same string ID plus ID minus ID, we have obtained two derivation, leftmost derivation and rightmost derivation. So this grammar is considered to be a ambiguous grammar. Hope you understand what is meant by ambiguous grammar. If a grammar has more than one parse tree, then that grammar is called as an ambiguous grammar. So let me tell with another example. So let me write the grammar first. E turns to I, E turns to E plus E, E turns to E star E, E gives E, and I turns to epsilon or 0 or 1 and so on up to 9. The string I am going to consider is 3 star 2 plus 5. Now let us check with first derivation. So E turns to E star E. I am starting it with this. Then I am replacing E with I star E as we have a production like this. Then I am going to replace I with 3 because I can be of any number. Starting from epsilon 0, 1, 2, 3 up to 9, I can be of any number. So I am going to replace I with 3 star E. Then the next leftmost non-terminal is E. So now I am going to replace this E with E plus E. So 3 gives 3 into E plus E. Then next I am going to replace this E with I. So 3 into I plus E. Next I am going to replace the non-terminal I with 2. Okay, because our string is 2. So 3 into 2 plus E. So the next step I am going to replace the next E. So 3 into 2 plus this E will be replaced with I. So this gives 3 into 2 plus this I will be replaced with 5. So this is our string. This is one form of derivation. Let us check with next form of derivation. So E gives E plus E. So first I am replacing this E with E star E. Next I am going to replace this E with I star E plus E. Next I am going to replace I with 3. So 3 star E plus E. Next I am going to replace this E with 2. So 3 into, next I am going to replace this E with I. So 3 into I plus E. Next I am going to replace this I with 2. So 3 into 2 plus E. Then finally I am going to replace the last non-terminal E with I. Then that I with 5. So 3 into 2 plus 5. So this is one form of leftmost derivation and this is one form of leftmost derivation. So for this grammar, we have obtained two leftmost derivation. So this grammar is what? This grammar is an ambiguous grammar. Ambiguity in grammar is not good for a compiler design. No method can detect and remove ambiguous automatically, but it can be removed by either rewriting the whole grammar or without ambiguity, or by setting and following associativity or precedence constraints. Let us discuss about what is meant by associativity and precedence. Associativity. If an operand has operators on both sides, the side on which the operator takes this operand is decided by the associativity of those operators. For example, if the operation is left associative, then the operand will be taken by the left operator, or if the operation is right associative, the right operator will take the operand. For example, operations such as addition, multiplication, subtraction and division are left associative. For example, if we have an expression like ID operator ID operator ID, so it will be evaluated as ID operator ID operator ID. So for example, ID plus ID plus ID, since they are left associative. And operations like exponentiation are right associative. That is, the order of evaluation in the same expression will be ID operator ID because it is right associative. See, for example, ID power ID power ID. So this is called as associativity. So we will consider the associativity of the operators. Next, precedence. If two different operators share a common operand, the precedence of operator decides which will take the operand. For example, if we have like this, 2 plus 3 into 4. So this can have two different passes, one corresponding to 2 plus 3 into 4 and another corresponding to 2 plus 3 into 4. But we can set precedence among the operators. By setting the precedence among the operators, this problem, that is obtaining two parse tree problems, will be easily removed. See, as in our previous example, mathematically multiplication has precedence over addition. We all know multiplication and division has higher precedence than addition and subtraction. So keeping that into consideration, this expression will always be interpreted as 2 plus 3 into 4. Okay, we won't consider this 2 plus 3 into 4. Always this expression will be evaluated in this manner. So these methods decreases the chances of ambiguity in a language or its grammar. Okay guys, hope you understand about today's lecture where we discussed about a simple introduction to parser and what are the rules of parser and what issues are faced by the parser. And finally, we have touched about context-free grammar where syntaxes of a programming language could be framed from it. And we have also discussed about parse tree, how a parse tree can be generated and what are the ambiguity that avails in the grammar and how to deal with that ambiguity using associativity and precedence. Lot of other techniques are also there for dealing the ambiguity of the grammars. Let us see the other techniques involved in removing the ambiguity in a grammar in our next lecture. Thank you all.